So we have x, we have f inverse of x. So to make my table, I'm just going to grab all the outputs for f. So 0.25, 0.5, 1, 2, 4, 8. And then all of the inputs of f are the outputs of my f inverse. So -2, -1, 0, 1, 2, 3. So now we can plot those points. And let's see. One there. 2, 1. 1, 2, 3, 4, 2, and then 8, 3. Do you think this is going to have an asymptote? Where? What now? Where? Which 0? So x equals 0? Good. So I have a vertical asymptote at x equals 0, which makes sense, right? Because our inverse just switches our inputs and our outputs. So our x values become our y values, and our y values become our x values. So if we have a horizontal asymptote at y equals 0, it would make sense if we're switching x and y, that would become x equals 0. Another way to look at it is we found with f of x that our y value could never be below 0 or equal to 0. So if all of the y values for f of x are x values for my inverse, then if I can never have a y value over here that's negative, then I'm never going to be able to have an x value over here that's negative. So I can never cross that y-axis. And so this guy is going to approach, whoops, that's not what I want to do, approach my y-axis. And then we're going to come up here and curve that way. So let's talk domain and range. What is the domain of f of x? So we're just looking at that black curve right now. Yeah, it's all real numbers, right? We have an arrow moving to the left, and we have an arrow moving to the right. It's a little tempting to wonder if maybe there's a vertical asymptote right there because it gets so steep. The way that we know that there's not a vertical asymptote is that I can put any number in for that exponent, right? There's not any number that I can't raise 2 to. And so there shouldn't be any number that x isn't equal to. So even though it gets pretty steep, and so it's not moving to the right really, really fast, it does eventually get really, really big. So -infinity to infinity. What about my range? Yeah, 0 to infinity, and we're not including 0, right, because we don't actually touch the x-axis. And so 0 to infinity, because that entire black curve is above the x-axis, so it only has positive y values. So then what's the domain of my inverse going to be? Which we can get by looking at the graph here of the blue curve, and also just by knowing that the domain of f is the range of f inverse, and the range of f is the domain of f inverse. So whatever my y values are, or can be, for f, is what my x values can be for f inverse. So then what's my range? Good. So -infinity to infinity. So the function that we just graphed with that blue curve is called the logarithm, in this case base 2. So it is written log, the base is a subscript, and then of x. And we can generalize this instead of doing this for 2, and pretty much everything stays exactly the same except for the particular x and y values. So if instead of 2 to the x, we call this a to the x, then the corresponding logarithmic function, so its inverse, is going to be log base a of x. And then in our table, we're not going to be able to get as many points, but the points that are especially helpful in actually graphing these guys are, we know that if we plug 0 in, no matter what our base is, raising anything to the 0 power gives us 1. And then a to the first power will always give me a. Good. And so that means the corresponding points on the graph of my logarithmic function are going to be, if we can get rid of this guy, just swapping the x and y values. So we get 1, 0, and a 1. So when you're asked to graph an inverse, I think the simplest way to do it is to graph the original function and then just make a table by swapping the x and y values. Like, you don't have to bother with like finding the inverse and then graphing it like as its own function. Just take the table that you made for your function and then swap your x and y values. So, and then nothing else changes. My domain, my range, my vertical asymptote, my horizontal asymptote, that is all the same regardless of what the base of my exponential function or my logarithmic function is. And in particular, you want to notice that the domain of a log function is restricted, right? So far we've only had 2 restrictions when we talk domains, right? There's a restriction when we divide, because you can't divide by 0. And there's a restriction when we take an even root, because you can't take the even root of a negative. And so far we've said those are the only times you're going to have a restriction on your domain. So those are the things you guys have looked for. Well, this is the third thing and last thing in this class that we will have to look at as far as restrictions on our domain. So the domain, to find the domain, of a logarithmic function. You want to solve the input greater than 0. So whatever you're taking the logarithm of has to be greater than 0. So for example, if I have f of x equals log base, I don't know, it doesn't really matter what the base is at this point, but base 5 of x minus 9. The input of the logarithm here is x minus 9. And so that's what I'm taking the logarithm of. So I have to solve x minus 9 is greater than 0 to find my domain, because we cannot take the logarithm of 0 or negative numbers. So x is greater than 9, and my domain is 9 to infinity. So it's very similar to finding the domain of a square root function, but notice it's a strict inequality. It's not or equal to. So it's strictly greater than 0. Okay, so let's formalize this definition of the logarithm. I need orange paper for this guy. Okay. So we're going to let a be a positive number. which is not equal to 1. So the reason that we say, there you go. The reason it can't be equal to 1 is that A corresponds to the base of our logarithm, which corresponds to the base of its inverse, which is an exponential expression. If I had 1 to the x, what would that look like? The function 1 to the x. Yeah, it'd be a constant function, right? It'd just be a horizontal line. So it wouldn't, if the base were 1, it wouldn't actually be an exponential function because 1 to any power is just 1. And so it doesn't behave like an exponential function. It's just a constant function. And so having a base of 1 doesn't really make much sense in terms of working with exponential functions and logarithmic functions. So that's the only reason we say it can't be 1. So we're taking any positive number and we say the logarithm base A of x is the exponent to which we raise A in order to get x. So in a lot of ways, the definition of the logarithm is similar to the definition of like a square root in the sense that it's defined recursively. So in terms of like what you do with the answer to get what you started with, right? Like, so to find the square root, we're like, what do I have to square to get this number? Here we're asking, what do I have to raise a to? What exponent do we raise a to in order to get this number? So the most important thing about this definition is that the logarithm is an exponent. So remembering that helps us a ton when it comes to the way that logarithms behave, because we have all these exponent rules. We know a ton about how exponents behave. If we can remember that a logarithm is an exponent, then all of a sudden we know a whole bunch about it because we know how exponents work, right? So really this definition will get you everywhere with logarithms. You can try to memorize the list of properties. It's long, but all of it just comes from this basic definition. And if you can just try to really understand the basic definition, you're going to be way stronger at this stuff than if you just try to memorize all these individual rules that are really easy to forget and mix up. So let's write this symbolically. Let's see, we say log base A. So that A is a subscript of x. Which is on the same level as the log. It's not an exponent. This is not A to the x power. The operation we're doing is log base A. The input of that is x. So the A and the x aren't like an expression of their own. The A is just a label on our logarithm to tell us the base of the exponential expression it corresponds to, or it's the inverse of. It's sort of like when we do radicals, like the index of the radical, right? Like the third root or the fourth root or the fifth root tells us which exponent it undoes. So that base is that same idea. It's just a label telling us which exponential expression it corresponds to. So log base A of x is equal to y if and only if well, we said that log base A of x is the exponent we raise a to in order to get x. So if we take a, we raise it to that exponent, we should get x. So those two equations are equivalent. They're saying exactly the same relationship, just in two different ways. One as a logarithmic equation and one as an exponential equation. This bit right here is the key to all of it. So everything we do with logarithms follows from this definition. So let's do a couple of concrete examples just so we can kind of see how it works. So if I want to evaluate log base 2 of 8, I'm asking myself to what power or to what exponent must I raise 2 in order to get 8? Or you could say 2 to what power? Is 8. When we read log base 2 of 8, that's what it means. It means what power do I have to raise 2 to in order to get 8? What's the answer to that question? 3. So log base 2 of 8 is 3 because 3 is the exponent we would raise 2 to in order to get 8. Let's do another one. Log base 5 of 1 over 25. Oops, evaluate. So again, 5 to what power? Is 1/25. So this one's not quite as obvious as the other one, right? Like 8, we can kind of look at it and be like, oh, I know that's 2 to the third. So if you're not sure, if you can't just look at it and know right off the bat what that exponent is, one good way to approach it is to try to rewrite your input as a power of your base, so as a power of 5. Can we write 25 as a power of 5? It's just 5 squared, right? So this is the same as log base 5 of 1 over 5 squared. But that's still not an exponential expression with 5 as the base, right? It's a fraction that happens to have an exponential expression in it. How can I make that not a fraction? So I can't do any of that because it's not an equation. So because I can't perform the operation on the other side of an equation to keep that balanced. But remember our exponent rules, right? What did we do to flip a fraction? Or take the reciprocal? What kind? Yes. Yes. You're such a rock star at exponents. Like you have been for like ever since I met you. It's amazing. Okay. So log base 5 of 5 to the negative 2 is the same as log base 5 of 1 over 5 squared. And so now when we look at it, we're asking the question, to what exponent would I raise 5 in order to get 5 to the negative 2? And the answer is negative 2, right? Don't overthink it. If you want to get 5 raised to the negative 2, you have to raise 5 to the negative 2, right? So the exponent is negative 2. So if you can get your input to be an exponential expression with the same base as your logarithm, then the exponent just gives you your answer. So sometimes we can look at them and know because it's fairly simple, but if not, you just want to work on rewriting your input with the base that your logarithm has. So let's talk a little bit more about the relationship between logarithms and exponential expressions. So where am I? There you are. the logarithm Hey, by the way, did you guys write down these questions, like in words? If not, it would be really helpful, I think. Okay. Yeah, at least one of them doesn't have to be both. Okay. It's just one of those things that like you think you'll remember, and then you get home and you to do your homework, and you're like, oh crap. Okay. So the logarithm base A is the inverse of the exponential function with the same base. And really, that's where logarithms come from. Their only purpose is to be the inverse of an exponential function, because inverses allow us to solve equations, right? We solve equations, like we undo multiplication by dividing on both sides. We undo addition by subtracting on both sides. We undo exponents by like the square root or the cube root on both sides. So logarithms give us an inverse operation so that we can solve equations that have a variable in the exponent. And really, that's their main purpose. I mean, there's some cool applications too. Log scales, like the Richter scale, and the, I don't know, the thing with the decibels, that scale, you know, like how loud things are, those are all log scales. So the way that they calculate those numbers is by taking the logarithm of a ratio. It's kind of cool. But the main purpose for us is that we will use this to solve exponential equations that have a variable in the exponent. And so really, its relationship to the exponential function is the most important thing about the logarithm. So symbolically, what we just said is that if f of x equals a to the x, then f inverse of x is log base A of x. So again, notice they have the same base. And so because we know they're inverses, we know that their composition is what? Composition of inverses is? Well, they undo each other, right? So if you start with x and you apply a function, and then you apply a function that undoes that function, you get x, right? It just takes you right back where you started. The composition of inverses is always x. So let's let f of x be 5 to the x, and g of x be log base 5 of x. What is f of g of x? It's x, yes. They are inverses of one another, right? So log base 5 is the inverse of the exponential function with base 5, which means that if I start with x, I apply g, and then f undoes g. So that gets me right back to x. So we know that that is true because they're inverses. But let's look at what it actually looks like if we evaluate this the same way we would evaluate any other composition. So if I want f of g of x, that is f of log base 5 of x. And so f says raise 5 to the input. So we have 5 raised to the log base 5 of x. So we want to evaluate this. And again, this is all just going to follow from the definition of the logarithm. And it's kind of a tongue twister, but if you can wrap your head around what we're about to say, like you've got this whole logarithm thing down. Like this is like the thing. So let's think about the definition of the logarithm. So log base 5 of x is the exponent to which you raise 5 in order to get x. Right? That's just the definition of the logarithm, exactly what we said when we first defined it. So if log base 5 of x is the exponent to which I raise 5 in order to get x, raising 5 to that exponent should give me what? Yeah, right? By definition, this entire thing, this logarithm, is the exponent on 5 that will give me a result of x, right? That's what this says, which means if I use that as my exponent, I have to get x, right? Just by definition. So raising 5 to this exponent gives us x. Like I said, it's a little bit of a tongue twister, but it's one of those things, if you read it over and over and really like ask yourself what it means, if you can get that, like you've got this whole log thing down. So we end up with what? X. We're gonna get a little bit. So far, so good? Did you guys write it down? Okay, let's go the other direction. Okay, so let's find g of f of x. What should g of f of x be? X, because we know that these are inverses of one another. But let's see why. So g of f of x equals g of 5 to the x. And g of x says take log base 5 of your input. So we've got log base 5 of 5 to the x, which is just asking us the question, to what exponent would you raise 5 in order to get 5 to the x? X, right? 5 to what power is 5 to the x? Well, x, right? And so we end up with x. This leads to our first couple of like properties of logs. Like I said, we're going to have a big list of these properties. Hopefully you guys believe me when I tell you it's going to be easier in the long run to try to understand where they come from than to memorize them. But I'm going to write them down just so you have them explicitly stated. So you might want to put them like on a different sheet of paper because we'll add to this list over the next couple of days. So properties of logarithms. This thing's real choppy. Logarithm. There we go. So we said log base A of a to the x is what? X. Because x is the exponent, you have to raise a2 in order to get a to the x. So x. And then a raised to log base A of x is x. Because log base A of x is the exponent you raise a to in order to get x. And then here's one, log base A of 1 is what? What power would you raise a to in order to get 1? 0, right? Anything to the 0 power is 1, so 0. And then log base A of A is what? 1. Very good. So those are our first few properties. We're going to add a lot more to those tomorrow. But for the rest of today, I want to just do some examples, like just concrete examples, similar to what you guys are going to do on your homework tonight. So you're really just working with all these logarithms. We need 2 more definitions of particular logarithms. So the common logarithm is what we call the base 10 logarithm, and we do not write the base. So f of x equals log of x. This is the common logarithm function, and it's base 10 logarithm. So it's sort of like the square root. We don't write the index of 2 because it's like the most common one. The same is true of the base 10 logarithm. So if you don't see a base written, so if there's no subscript, it's assumed to be 10. And then the other one we have is actually more common than the common logarithm. We use it more often. It's called the natural logarithm. And it is base e. Oops. Remember, we talked about e the other day. E is the constant that's going to allow us to do continuous exponential functions. So because we use those so much in exponential functions, it's really important that we have a logarithm that will undo. So is the inverse of that e to the x function. And so it also has a different notation. It is written ln of x. So that's an L, not an I or a 1. So ln of x means log base e of x. And you'll notice on your calculator, those are the 2 buttons that you can see. I mean, you could do any base logarithm on your calculator on these new guys. They're pretty fancy. But if you look in the left-hand column, like the 6th one down, I believe, says log, and that is the common log, so base 10 only. And then like the 7th one down says ln, and that's your natural log. Okay, let's evaluate. However, you guys aren't going to use your calculators tonight. I mean, you might, but you're only hurting yourself. They will come in handy, though, when we start solving equations. I mean it, like when we throw, like, when we get rid of all the numbers, all of a sudden, if you've been, like, punching buttons on your calculator, you're like, what the heck's going on? Okay. We'll start with writing, we're going to just rewrite logarithmic equations as exponential equations and vice versa. So just using that definition to go back and forth between exponential form and logarithmic form is one important thing to know how to do with logarithms. So we are going to write as a logarithmic equation. So first one, we've got 16 equals 2 to the x. We are not solving anything here. We are not evaluating anything here. We're just rewriting the equation. So the key to these is just remembering that the logarithm is equal to the exponent. So the base is always the same. So here the base of my exponential expression is 2, which means that's going to be the base of my logarithm. So this is log base 2, and then the logarithm is equal to the exponent. And then there's only one place for the 16 to go once we've done that. So log base 2 of 16 is equal to the exponent. We raise 2 in order to get 16. If you can remember the log is equal to the exponent, that's probably the simplest way to remember where everything goes. So let's do a couple more. Let's do e to the t equals 70. So my base is e, which means I'm going to use what?
ln.
Yep, the natural log. So ln of something is equal to my exponent, which means this has to be 70. Another way you can think of it is that like the output of the exponential is the input of the logarithm and vice versa, right? So the exponential expression is equal to 70, and so 70 is the input of my logarithm. The exponent over here is t, and so my logarithm is equal to t. Notice there's no subscript on that ln, so ln is only used for base e, so we don't need any subscript on it. So let's go the other direction. Let's write as an exponential equation. So let's see. Log of 0.001 equals -3. So what's my base here? Yeah, it's going to be 10 because that's the common log, right? There's no subscript, which means an implied base of 10. So the base of my exponential expression is 10. What is my exponent? Remember, the logarithm is equal to the exponent. So -3 equals, yep. And like I said, like one of the reasons we do this with numbers first is just so you have a concrete example. So like you can look at this and know if you're right or not because you do 10 to the -3rd, and if you don't get 0.001, you probably wrote it wrong, right? So like we purposely try to do a bit with numbers just so you can make sure that you're doing things right based on what you know about how the numbers relate. Let's do, how about log, or x equals log base 2 of m. What's my base? 2, very good. What's my exponent? Good, because the logarithm is equal to the exponent, regardless of what side it's on. And then that's got to be equal to m. So I kind of think of these as like having like 3 components, right? So there's like the base, the exponent, and then the other thing. And so if you can remember the base is the same either way, then that takes care of that. The logarithm is equal to the exponent, that takes care of the exponent, and then the other number just is the other number. Ooh, we have time for another one. Let's evaluate a couple. I love logarithms. They're my favorite. Evaluate, they're like puzzles. Let's do, oh, this is good. Log base 2 of the cube root of 4. So the question is, 2 to what power gives me the cube root of 4? I mean, I don't know that off the top of my head, do you guys? So that's okay. Let's rewrite our input, the cube root of 4, with a base of 2, if possible. So can we write 4 with a base of 2? Like as an exponential expression? The number 4?
Wouldn't that equal 8?
2 times 2 equals 4.
Yeah, 2 squared is 4, right? So this is log base 2 of the cube root of 2 squared. And then do we know how to write the cube root as an exponent? I mean, we do. Do you guys remember how to write the cube root as an exponent? So the square root is the same as raising to the power of 1/2. So the cube root is the same as raising to the power of 1/3. Good. So this is log base 2 of 2 squared to the 1/3. But if we have an exponential expression raised to another exponent, what do we do with those exponents? You guys know this? Don't let the fact that there's a log in front of it make it more daunting. What do I do with the 2 and the 1/3? Yeah, we multiply them, right? We only add if we're multiplying 2 raised to some power times 2 raised to another power. So we have log base 2 of 2 to the 2/3, which is equal to what? What exponent do I have to raise 2 to in order to get 2 to the 2/3? It's a lot of 2's. 2/3, good. So once you've written your input as an exponential expression with the base of the logarithm, then the answer is just the exponent. Because that comes right back to like this little rule that the log base a of a to the x is just x. So if we can write our input with base 2, then our answer is just our exponent. Talk to yourself out loud when you do this. Nobody's listening. Nobody's going to watch.